Have you ever been somewhere like a museum and seen a vehicle with square wheels rolling on some bumpy-looking terrain? The idea is the shape of the terrain has been carefully designed to give the square wheel a smooth ride. Meaning, if you were to ride the square-wheeled vehicle, you wouldn't feel any bumps or jolts. It would feel pretty much like riding an ordinary vehicle with circular wheels on a flat road. This should ignite all kinds of questions. What exactly is the shape of this special road? And how would you find it? And what about other wheel shapes besides squares? Can you do the reverse and find the perfect wheel for any given road? Well, my plan is to explore and answer all of these questions and more in a series of videos, of which this is the first. And hopefully on a deep enough level that you'll be able to explore these questions more on your own once we're done. For this video, the plan is to solve the general problem of finding the perfect road for any given wheel to roll on using a couple of basic observations about the nature of rolling. We'll then apply the solution to determine the perfect road for a square wheel. The following one or two videos will look at the interesting roads that other shapes of wheel produce, the inverse problem of finding a wheel from a road, and extending the results to the problem of designing two gears that mesh well with one another. Alright, enough with the introduction. Without further ado, let's get this ball rolling. First, what makes this problem so complicated? Consider the square wheel again. If you think about it for a bit, you might be able to get a loose idea of what the road would have to look like. Since the radius of a square wheel is bigger near a corner point, you would expect the road would need to periodically dip down when the wheel rolls near a corner in order to accommodate the increased radius of the wheel. But figuring out the exact shape of the road so that the ride is perfectly smooth is a pretty tricky problem. There are a lot of interdependent dynamics going on when a shape rolls on another shape. For example, as a wheel rolls, it rotates of course, but the amount it moves forward depends on the shape of the road. Flatter roads give more forward horizontal movement than steeper ones. And besides that, the curvature of the road also contributes to the rotation of the wheel. Because as the road curves, the wheel must rotate an additional amount to ensure its rim always stays tangent to the road at the contact point. That's a lot to keep track of. And yet, as you'll see, it takes just a couple of seemingly unimportant observations about the geometry of rolling to tame these complexities and derive a surprisingly simple pair of equations that you can use to compute the ideal road for any shape of wheel, not just square wheels. But first, it's worth clarifying something that's been a bit vague so far. We're trying to find the road that gives any shaped wheel a smooth ride. But what exactly do we mean by a smooth ride? How exactly would you determine that a wheel will give a rider a smooth ride over a given road? Well, take an ordinary circular wheel rolling on a flat road. It gives a smooth ride. Why? Because the point where the wheel is attached to the vehicle, the axle, only moves horizontally. Every other point on the wheel is spinning to some degree or other, and so wiggles up and down a bit. But the axle is unique in that it never wiggles in the vertical direction. Its path through space stays on a horizontal line. So I take it that a wheel gives a smooth ride over a given road if there exists some point inside of it, let's call it the axle, which always stays confined to a single horizontal line as the wheel rolls on the road. Okay, with that out of the way, let's take a look at our first observation about rolling. Take a look again at the square wheel rolling on its ideal road, and pay attention to the relative positions of these 2 points in the system: the axle, and the point where the wheel meets the road. Notice anything? You might notice that these 2 points always lie on a vertical line. No matter where we find the wheel, the axle is always directly above the contact point. And this isn't just a quirk of square wheels either. It's true of all wheels rolling on roads that keep the axle on a horizontal line. Why is that? This is actually a consequence of a more general property of rolling that I call the orthogonal motion property, and it says the following. If you draw a line between the road wheel contact point and any point attached to a rolling wheel, that line will always be perpendicular to the attached point's path of travel as the wheel rolls. To put it another way, any point attached to a rolling wheel always moves in a direction perpendicular to the line currently connecting it to the road wheel contact point. It turns out the details to prove this are a bit messy, or at least the proof I came up with was. I'll briefly put this proof on screen so those of you who want to can pause and look at it. Despite the algebraic blood and gore, I actually really like this proof for how it makes use of complex numbers to capture geometric ideas, and I think it's a great mini-example of why complex numbers are worth learning. However, you can actually understand the orthogonal motion property without any of that on a fairly intuitive level too. It's basically saying that rolling motion locally resembles pivoting motion. To see what I mean, imagine fixing in place the current road wheel contact point for our wheel. So rotating the wheel no longer causes it to roll, it just makes it pivot around this anchor point. Which means every point on the wheel moves perpendicularly around the anchor point in a circle. But the idea is that for small movements, rolling the wheel and pivoting it about a point look similar. So you can think of the orthogonal motion property as arising from the fact that, for small movements, rolling looks like pivoting, and pivoting means all points move in a direction perpendicular around the anchor point. For this reason, I sometimes like to call the orthogonal motion property the pivot principle. But however you look at it, this property explains why the axle is always above the contact point for a wheel giving a smooth ride. The axle's path of travel is horizontal. That's what we decided smooth ride meant. So the line connecting the axle to the road wheel contact point must be perpendicular to this horizontal line, meaning it's vertical. This fact will come in handy soon enough, but for now, I want to direct your attention to our second observation of the nature of rolling. For a wheel to roll without slipping on a road, the rim of the wheel must be stationary at the exact point where it contacts the road. Meaning, if you track the movement of a single point on the rim, then when that point comes into contact with the road, its speed will be 0 at that exact moment. Which should make sense, right? After all, if the rim were moving relative to the road where it touches the road, the wheel would no longer be rolling, but slipping on the road. So those are our two observations. One, that the axle of the wheel and the road wheel contact point always lie on a vertical line. And two, the rim of the wheel is stationary relative to the road at the point of contact. But how do we use these two observations to determine the shape of the road that gives a wheel a smooth ride? Well, to do that, we'll need to package these two observations into the language of mathematical equations. But to do that, we'll need a mathematical description of our road and wheel. Let's start with the road first. In order to give it the most flexible description we can, let's describe it parametrically. That means writing both the x and y coordinates of points on the road as a pair of coupled equations that depend on a parameter we'll call t. The idea behind parametric equations, if you're unfamiliar, is instead of picking a value for x and solving for y, or vice versa, in order to generate a point on the curve, you instead pick a value for t and plug it independently into both the x and y functions to generate an xy pair. The collection of all the points you get from plugging in all possible values for t is the curve the parametric equations describe. So we'll plan to have a parametric description of the road. We don't know what it looks like yet, of course, but we'll expect to get a parametric result. Let's do the same thing for the wheel. But in this case, instead of describing a point on the wheel using an x and a y coordinate, it'll be helpful if we instead characterize it using polar coordinates. Meaning in terms of a radius function r of t, which represents how far the given wheel point is from the origin, and an angle function theta of t, which represents its counterclockwise angle away from the positive x-axis. You'll see later why this polar representation is useful, but for now, perhaps it doesn't come as a surprise that it might, since it's the wheel that's rotating in this problem. Alright, so we've got parametric representations of both the road and wheel, but notice that these functions are still pretty underspecified. To better set the stage for solving our actual problem, let's impose a few more constraints on these curves. First, remember that the axle of our wheel must stay confined to a horizontal line throughout the rolling motion. That's our smooth ride property. So let's make the x-axis be that horizontal line. That will mean our road curve will always lie below the x-axis. Or in other words, the y function for our road will always be negative valued. Second, since the axle of the wheel plays such a, pivotal role in this problem, let's place it at the origin of the wheel's local coordinate system. So the curve represented by our wheel parametric functions should always have the intended axle point located at the origin. Finally, let's give an interpretation to the parameter t. Let's say t represents time, and the point you get out from plugging in t to either the road functions, x and y, or the wheel functions, r and theta, represents the location of the road wheel contact point at the current time t. So the point xy is where the contact point is on the road curve, and r theta is where the contact point is on the wheel curve. And these will move in sync with one another as you vary the time t. Alright, with all this groundwork in place, we're ready to solve our problem. As a reminder, our goal is to determine the ideal shape of the road for any given wheel, so that the wheel's axle stays confined to a horizontal line. So in terms of the functions we have, our goal is to find the two road functions, x of t and y of t, given knowledge of the two wheel functions, r of t and theta of t. To do that, we need to find some relationships between these two sets of functions. However, before we do that, let me take a minute to address a possible misconception here. Based on how I named them, you might be tempted to say that x and y relate to r and theta via the standard polar rectangular conversion formulas. But that wouldn't actually work here, because in this context, x and y, and r and theta, describe two completely different curves. It's just an accident of the names I picked for these variables that they look related in that way. Maybe it would have been better if I subscripted each variable's name with either road or wheel to make it completely clear which curve each variable is describing, but I dislike the notational clutter that introduces, so I prefer to omit them. Just remember that, despite their names, x and y, and r and theta, are describing two separate curves, and are therefore not related to each other via the usual polar formulas. Instead, they're related via the two observations about rolling we made earlier. So now let's apply them both in turn. Let's start with the vertical alignment property. It says that the axle of the wheel and the road wheel contact point always lie on a vertical line. Since by convention we required the axle to stay confined to the x-axis, it means the distance between the axle and the road wheel contact point is just the y-coordinate of the contact point. Or at least that's what it is in road space. If we look in wheel space instead, the axle is always located at the origin, and so the distance between the axle and the contact point in wheel space is simply the contact point's distance from the origin. That is, our function r. So from comparing the distance between the axle and the contact point in both road space and wheel space, we get a relation between the road and wheel. At any time t, the depth of the road, y, is equal to the radius of the wheel, r. So y equals r. Well, almost. Technically, r of t should have a negative sign in front of it because the y-coordinate of the road needs to be negative since the road lies below the x-axis. But that's a quick fix. However, this equation is only half the story. It only tells us how to find the y function of the road from the wheel. We still need to figure out how to find the road's x function from the r and theta wheel functions. That requires a subtler argument that leverages our second observation, the stationary rim property. Remember that this property says that the rim of the wheel is stationary relative to the road at the exact point where it makes contact with the road. However, if you change your reference frame and instead watch the motion of the rim relative to the axle, you would find that all points on the rim are constantly in motion. Now, since the rim is stationary relative to the road where it makes contact, but moving relative to the axle, it must mean that the rim speed relative to the axle is equal to the axle speed relative to the road. To put it another way, in shifting your reference frame from that of the road to that of the axle, you find the stationary rim at the contact point inherits the speed of the axle relative to the road. But now think about how we can compute these two different, but actually equal, speeds in terms of the road and wheel functions. The speed of the axle relative to the road is the same as the horizontal speed of the contact point along the road, because the axle always stays directly above the contact point. This horizontal component of speed can be written as the time derivative of our variable x, where, you remember, x represents the horizontal component of the road contact point's position. As for the speed of the rim relative to the axle, if you've taken some physics, you might know that you can compute the speed of an object moving in a circle by multiplying the radius, r, by its angular speed, the rate of change of the angle it makes with the center point. In this case, that would be equal to the time derivative of theta. And so, setting the axle speed equal to the rim speed, we get a second relation between the road and wheel. The derivative of x is equal to r times the derivative of theta, a differential equation that gives us a way to solve for x given r and theta. Of course, solving this fully for x is not as straightforward as it was for y, as you'll have to integrate r of t times the derivative of theta of t, but all things considered, it's not that bad, especially with computers able to do most of the heavy lifting. In fact, let's go ahead and do it. Let's use these two equations to finally figure out the exact shape of this bumpy road that a square rolls on. To use these two equations, we first have to have a parametric description of the wheel. In this case, it's a square with the axle located at its center. And let's say that its dimensions are 2 by 2, so each corner point is located at plus or minus 1, plus or minus 1. Unfortunately, a square is not the easiest thing to write a parametric formula for, and it wouldn't be easy to manipulate even if we did. But the good news is, we don't have to. A square is just 4 line segments glued together, so instead of modeling the whole square, let's just model one of its sides. Now, we can orient this line segment anywhere we like in wheel space, as long as the axle stays fixed at the origin. But it turns out the algebra will be easiest if we make the line segment a vertical line that lives in the right half plane, with its lower end at the point 1, -1, and its upper end at the point 1, +1. Now this is really easy to parametrize. We can just set the x-coordinate constantly equal to 1, and have the y-coordinate equal to the time t. And if we have t vary from t equals -1 to +1, the points we get trace out the line segment we want. Now, I said this was easy, and it was, but as you might have noticed, we can't actually use this parametrization directly for our road-wheel equations because we need to have a polar representation of the wheel, meaning in terms of r and theta. Right now, we have a rectangular representation in terms of x and y. But it's not too hard to convert over. We can use the standard polar rectangular conversion formulas to convert x and y to r and theta. And to be clear, this time it's okay to use these formulas because the x and y I'm starting with, and the r and theta I want to end up with, are meant to describe the same curve, the wheel. R is the easiest one to find. To find r from x and y, it's basically just the Pythagorean theorem. R equals the square root of x squared plus y squared. And since x is 1, and y is t in this case, it becomes square root of 1 squared plus t squared, or just square root of 1 plus t squared. Very nice. As for theta, with a little trigonometry, you can find that the tangent of theta is equal to the fraction y over x, meaning theta is the arctangent of y over x, which in this case is t over 1, or just t. So we now have our polar representation of the wheel, which means we can plug the equations in to our road-wheel equations to solve for the road functions x of t and y of t. The formula for y is easy. It's just -r, so negative square root of 1 plus t squared in this case. X is a bit more involved. To find it, we'll need the derivative of theta with respect to t. That can be done. The derivative of arctangent of t is 1 over 1 plus t squared. Multiplying this by our formula for r and simplifying, we get that the derivative of x is equal to 1 over the square root of 1 plus t squared. Integrating it, we get that x is equal to something called the inverse hyperbolic sine of t, a function I'm sure all of you have heard of before. But whatever, putting it together with our formula for y, we get a parametric description of the road. Ta-da! I hope you're happy. Yes, the sound of your applause is deafening. Okay, admittedly, this is not a very satisfying final answer. It's kind of a mess. But actually, it turns out it simplifies quite a bit if we turn these parametric equations back into a simple Cartesian equation by eliminating the parameter t. If you solve for t in terms of x, and plug it into our formula for y, you get that y is equal to the negative square root of 1 plus the hyperbolic sine function squared of x, which turns out simplifies into just negative cosh of x, where cosh is this thing called the hyperbolic cosine function. This is a function you might not have heard of before, but it actually has a pretty simple algebraic definition. It's the mean value of e to the x and e to the negative x. That is, it's the average of the standard exponential growth and decay functions, and its graph is a curve known as a catenary. You might not have heard of a catenary curve before either, but you've almost certainly seen one before. It's the shape a chain or string takes when you hang it limp from 2 points. You can see them in power lines, or rope fences. And so it turns out a catenary, or rather, an upside-down catenary, is the ideal shape of road for a line segment to roll on. And if we string together multiple of these catenaries, we get the road that a square wheel will roll smoothly over. Isn't that neat? But I don't want to end off this video on that note, because although we did indeed find the ideal shape of road for a square wheel to roll on, we got it through the pretty opaque and magical-seeming process of algebra and calculus. No, I want you to feel what these equations are really doing a bit more, and how they define the shape of the road. To see visually, step by step, how these equations generate the road from the wheel. Take our square wheel again and place its axle at the origin. But this time, let's start it off rotated by 45 degrees so that its bottommost corner is the initial point of contact with the road we're going to build. Let's say this is time t equals 0. Now consider increasing the time t by a very small amount, like 0.001 or something, and call it dt. This would cause the would-be contact point on the wheel to move slightly along it in the counterclockwise direction. We know from the vertical alignment property that the contact point should always be directly below the axle, so rotate the wheel so that the new contact point does that. Notice how the new contact point is a little higher up than the old one. Its height reflects the required road height after this small rotation of the wheel. That's what our first road-wheel equation says. However, we don't yet know how much the wheel needs to move forward in response to this rotation. So all we really know right now is that the next point on the road has to be somewhere on this upper horizontal line. To determine how much to move the wheel forward, go back a step to the initial orientation of the wheel. Now consider the distance this new contact point travels when rotating the wheel to get it situated below the axle. See that little arc right there? The length of that little arc is the distance we need to horizontally shift the wheel. It represents r times d theta, where d theta is the tiny amount the wheel rotated. And according to our second road-wheel equation, if we cancel the dt's, the distance the wheel needs to move horizontally, dx, is exactly r times d theta. So if we take the length of this arc and shift the wheel forward by that length, we get that this blue point right here, where the new contact point on the wheel ends up, is a new point on our road. So let's connect it up with our initial road point, and we've just generated a small segment of the road. Do you get the idea? After this, just repeat the process. Increase the time t by a little bit more, see where the new contact point needs to be on the wheel, rotate the wheel until this new contact point is below the axle, shift the wheel forward by the distance the new contact point traveled during rotation, and connect the point the contact point lands on to your road curve in progress. And just continue like this, over and over, and gradually, the road will take shape. Okay, maybe this road doesn't look quite like it's supposed to. I mean, it looks kind of jagged and rough, not at all like the smooth curves I've been showing you before. But that's just because the step size dt I used was actually relatively big. The shape of the road will look more and more correct the smaller step size you pick. And in the limit, you get the same catenary curve we saw earlier. Woo! So there we have it. We've seen how to derive a pair of equations that let you determine the ideal road for any shape of wheel to give a smooth ride. And we applied these equations in two separate ways to find the ideal road for a square wheel, which turned out to be a chain of upside-down catenary curves. But there's still so much more to explore. What road shape would a triangle produce? Or a hexagon? What about a wheel that's not a polygon at all, like an ellipse or a parabola? And what about the inverse problem of finding the ideal wheel for a given road? How would you find the wheel that rolls smoothly on a road shaped like a sine wave, or a sawtooth? I hope to explore these questions and more of the fascinating world of roads, wheels, and rolling in the next 1 or 2 videos. But until then, I encourage you to ponder and explore the topic yourself. And if you're so inclined, try to apply what we covered in this video to discover some things of your own. I think you'll be in for some fun surprises.